Alright, what's up y'all? Welcome back to Structure Free Learning. And in this video, we're going to do 4 example problems showing you how to calculate support reactions of simply supported beams. Our approach involves drawing a free body diagram and applying equilibrium equations. So let's take a look at our first example, which is a simply supported beam. So first I'm going to draw my FBD. And drawing the FBD involves identifying what kind of supports that you have for the beam. So here at A, I have a pin support that restricts movement of the beam, like left to right and up and down. So there's forces that restricts the motion. So if it's a displacement that it restricts, and if it's a rotation that's restricted, then I have a moment reaction. So the pin at A got a horizontal reaction, AX, and then a vertical support reaction, AY. Here at B, I have a roller support. It's allowed to move left and right. We'll say that this roller here restricts motion up and down. So we have a vertical force reaction. I can draw these support reactions in any direction that I want. And now I'm going to apply my equilibrium equations. For my equilibrium equations, I'm going to use a global coordinate system. Forces pointing to the right are positive x. Anything pointing up will be positive y, and any rotations according to the right-hand rule will be positive moments. We have 3 equilibrium equations, which means that we can only handle 3 unknowns. And in this case here, I got ax, ay, by. That's 3 unknowns. And I have 3 equilibrium equations. That means I can solve it, and this is what we might call statically determined. For a first course in statics and in mechanics of materials, typically this is enough. If you ever find yourself with 4 unknowns, you should probably means that you need to either think about something or you need to think about how to solve for a statically indeterminate structure, and that's going to take some more advanced techniques. So here, for my equilibrium equations, the first one I'm going to apply is sum of the forces in the horizontal, and this one is kind of trivial. And sum of the forces in the x equals 0, and that the only thing I have pointing in that direction is ax, and this tells me ax equals 0. I'll apply sum of the forces in the vertical. I've got ay pointing up. I've got this first 3 kilonewtons pointing down, so that's negative 3 kilonewtons. The next 3 kilonewtons is pointing up, so that's a positive 3 kilonewtons. And then I've got my support reaction at B, positive by equal to 0. This tells me that ay plus by equals 0. It's still one equation with 2 unknowns, so I need one more equation, which is going to be sum of the moments. I can take sum of the moments about any point. I'll choose to take sum of the moments at point A, and ax and ay go through point A, so it doesn't cause a moment about A. This first 3 kilonewtons causes a negative moment about point A, or it's going clockwise. The moment is going clockwise about A, so this would be negative 3 kilonewtons. Force times distance of 2 meters. The next 3 kilonewton concentrated force causes a positive moment about A. That's 3 kilonewtons, and the arm, the distance to point A is 4 meters plus by times the total distance of 6 meters equals 0. And using this, I see I've got one equation, one unknown, and when I solve for that, by is, I get by is negative 1 kilonewton. And what that means is, compared to my original drawing, I had drawn by pointing up. That negative result actually means that by is 1 kilonewton pointing down. And then when I go back and I substitute into this sum of the forces in the y, I'll get ay plus negative 1 kilonewton equals 0. And that tells me ay is positive 1 kilonewton. And that positive means that the way I drew ay initially pointing up is good, and so that's just 1 kilonewton pointing up. And I can redraw the entire beam with support reactions drawn in. And this would be my beam with the support reactions drawn in. All right, let's do another example. So first I draw my FBD. I've got this pin support on the left, so it's got a vertical and a horizontal support reaction. I've got this roller support at B, a vertical support reaction. I've got 3 unknowns. I got 3 equilibrium equations, so I'm good to go. And from sum of the forces in the horizontal, I know that ax is 0. So now let me take sum of the forces in the vertical. This will be ay. I've got to deal with this distributed loading. So what we know about distributed loads is that the area under the distributed load is a force resultant. And so I could look at, I could break this up into 3 areas. I could start with this right here. I could say this area here is 1/2 base times the height. which is equal to 3 kips. And then this rectangular distributed load, the force resultant will be right here. And this will be the area under the distributed load, which will be 2 times 4. This will give me 8 kips. And then I look at over here, this last area, right, is the same as the other, 1/2. And this is also going to be 3 kips. And so by equilibrium, I could do sum of the force in the vertical. It'd be AY minus 3 kips minus 8 kips minus the 3 kips. I've got these additional concentrated forces. So minus 15 kips minus 15 kips plus BY equals 0. And this equation, sum of the force in the vertical, will tell me that AY plus BY is 44 kips. And then I want to take some of the moments about A here, and then I got to find the resultant. And the resultant of all my distributed loads acts through the centroid of the area. So this first triangle, the resultant acts through this point here, and this distance would be the centroid of the triangle, which would be 2/3 of its base. 2/3 times 3 feet. And then here, the center of this resultant, from this end right here from the beginning, the centroid would be at 2 feet, right in the middle, halfway. And then similarly here, I could say, oh, the location of the resultant here is 2/3 from its thin end. So this would be 2 feet and 1 feet here. And so when I apply some of the moments, I could go through, and if I take moments about point A, I'd have, let's see, this 3 kip, the purple force resultant would be causing a negative moment, negative 3 kips times 2 feet is the arm, minus the 15 kips times 3 feet, minus the 8 kips times 5 feet, minus the 15 kips times 7 feet, minus 3 kips times 8 feet, plus BY times 10 feet equals 0. And when I solve this out, I'll get that BY is 22 kips, which means I have 22 kips pointing up. And then when I plug and chug into my sum of the forces in the Y, I will get that AY is also 22 kips pointing upwards. Maybe something you recognized much earlier is that you'll notice that knowing AX is 0, we notice that all the external loading on the structure is symmetrical. I have a line of symmetry right down the middle here, and that means half the load goes to AY, half the load goes to BY. So if you can recognize the symmetry, then you know half will go to the left and half will go to the right. All right, so let's do another example. This example is a little bit more complicated. It's got this linearly distributed load that looks like a trapezoid. I've got a pin support at A and a roller support at B. And those are my support reactions. I'm going to apply my equilibrium equations. From sum of the forces in the horizontal, I know right away AX is 0. And let's see here, I'm going to apply sum of the forces in the vertical. And let's see, going left to right, I've got AY. Now this trapezoidal load, I'm going to break up into 2 parts. I'm going to break up into the rectangular part and the triangular part, like this. The force of the rectangular part, which is in orange, the force is the area of that rectangular piece, which is 12 kilonewtons per meter times 6 meters. And this triangular part is here. Force from there is the area of that blue triangle. This part right here is 18 minus 12. This is 6 kilonewtons per meter. The force from the linearly or the triangular portion of the load is minus 1/2 the base, which is 6 meters, times a height of 6 kilonewtons per meter. And then I add the BY and minus the 20 kilonewton concentrated force at the end, C. And when I write all this out, I'll get 2 unknowns, 1 equation. And then I got to take the sum of the moments about a point. I'll take moments about point A. And it's here, because I broke up the loading, the resultant of the orange or the rectangular portion of the distributed load is right in the middle right here. That has a resultant of 12 times 6, which is 72 kilonewtons. And it's right in the middle. So from point A, it is 3 meters away. The linearly distributed part, the triangular portion, has a resultant that's going to be right around here. And it's going to be 18 kilonewtons. And the resultant is 2/3 of 6, 4 meters. And that makes this distance 2 meters. That some of the moments about point A will be negative 72 times 3 meters minus 18 kilonewtons times 4 meters plus By times 6 meters minus 20 kilonewtons times 9 meters. All this equals 0. And I'll have one equation, one unknown here, and I can solve for By. Now again, By is positive 78 kilonewtons, which means it's 78 kilonewtons pointing up. Yes. And then I just plug that back into some of the forces in the vertical direction. And that will tell me that Ay is... And I get a positive result for the Ay of 32 kilonewtons, which also means it's pointing up. And those are my support reactions. And I can redraw the beam with the support reactions drawn in as well. And I could use this geometry that I've drawn here, the beam with the loading, to draw the shear moment diagrams. All right, one more example, yes! All right, so I've got here this beam ABC. It's pin supported at A, and then it has this rod BD connected to it, holding it up. A lot of times students will take this diagram, they'll see the two pin supports at A and D, and they'll end up drawing this. And what we'll have here is 4 support reactions, and it will seem like it's unsolvable. What we have to recognize here is that member BD is a truss element, and we can assume it's a truss element, meaning that it only has an internal normal force on the inside as long as the member is pinned at its ends, and there's no loading or transverse loading along the length of the member. Basically, there's nothing on member BD that can make it bend. So if I can recognize that member BD is a truss element, then I can cut away, or I can kind of expose the internal loading in member BD here, and I would have an internal force acting at point. I would have this normal force acting on BD, just like we did in method of joints. And this force, is like a line of action through point B. And this free body diagram that I'm going to be dealing with is essentially here, outlined in purple. This is the free body diagram I am considering here for my equilibrium equations. I'm going to apply some of the forces in the X. This time, some of the forces in the X is not trivial. It's actually of value. Some of the forces in the X, I'd have AX minus the horizontal component of NBD minus NBD cosine of 30 degrees equals 0. So that's one equation, 2 unknowns. Then I would do some of the forces in the Y equals 0. And this would tell me that AY plus the vertical component of NBD, which would be NBD sine 30, minus the area of the distributed load, which is, or the resultant of that distributed load, which is 4 kilonewtons per meter times 3 meters. Equals 0. Again, this is 2 unknowns, 1 equation. So I definitely need that moment equation for sure. I'll take moments about point A. Here I would have, the resultant of the distributed load here, and the resultant would be halfway. So here, where this distance would be 1.5 meters, where the centroid of that area is, and that 12 kilonewtons, or the resultant of the distributed load, causes a negative moment. And then this NBD, which is acting through point B, the vertical component of NBD, causes a positive moment around A, so plus NBD sine of 30 times 2 meters equals 0. And I can use this equation to solve for NBD, positive 18 kilonewtons, and I can go back and just plug and chug. And if I were to draw a free body diagram of ABC with the support reactions and NBD drawn in, it would look like this. So here's a free body diagram of ABC, and then I could look at member BD. And then if I really wanted to find dx and dy, it's really just about breaking up the vector into components. But here, I'd have this right here, and then equal and opposite this connection. I'd have 18 kilonewtons here. And then this joint, I would have dx and dy like this. And I would just look at equilibrium of this joint right here. And this would tell me. And really, for joint equilibrium, I just have some of the forces in the X and some of the forces in the Y. the negative 15.58 just tells me that dx is actually pointing to the left. And then once I do some of the forces in the y, this tells me that dy is 9 kilonewtons, which means, and we get a positive result, meaning that dy is pointing up. So these are all my support reactions. The really important part would be this beam right here, ABC, especially if I want to draw the shear moment diagram for ABC. All right, hopefully this was a good overview of calculating support reactions for simply supported beams. Check out the next video, which is going to be covering cantilever beams. Yes! Talk to you later. Structure free.